Welcome everyone to this webinar on attack tree analysis. My name is David Wiseman. I work in technical support and customer training for Isograph in the UK. Today's webinar, again, is being recorded, so you can watch at a later date. We will also be taking questions at the end of the webinar via the chat menu in the GoToWebinar console that should be on your desktop. Today's webinar will be covering attack tree analysis, how we use that to understand and model threats using appropriate software tools. So I'd just like to begin with a short agenda to give you an idea of the things that we'll be talking about today. We'll begin, of course, with an introduction to the concept of attack tree analysis and how that relates to maybe some more familiar analysis techniques. Things like fault tree analysis, for example. We'll then take a look at a case study based on a couple of papers that were presented at conferences in 2015. And we'll then use those cases as the foundation for building a basic model of an attack tree in software. And we'll use that to kind of explore some of the familiar aspects of constructing the model, which those of you familiar with fault trees may recognize, but also some of the areas where attack trees deviate from the way fault tree analysis is performed. And then, of course, at the end, we'll have a conclusion where we sum up the learning points from today's webinar, after which we'll take some questions on the things we've looked at today. So to begin with, let's talk a little bit about attack tree analysis. Now, of course, a number of you may already be familiar with the concept of a fault tree analysis. In fault tree analysis, we look at determining the causes, the probability, and or the frequency of a hazard due to failures and conditions within a system. Of course, in today's interconnected world, we now have to start thinking about hazards that might arise due to deliberate attacks. And this is something that I think has become more and more prevalent. Certainly, if we look at news stories in today's press, we see an awful lot about cyber attacks against various individuals and institutions. And this is an area where an analysis technique like attack tree can really excel in helping us to understand those threats, determine the causes and the risks posed by those threats, and also how we might go about mitigating them as best we can. Now, attack trees were first described in the 90s, and it's an analysis technique that is fundamentally based on the fault tree analysis technique. You should be able to see to the right of the slide there, there is a simple example of an attack tree. Here, the hazard is the occurrence of fraud in a system, and anyone who's familiar with a fault tree will probably recognize the structure there, consisting of logic gates, basic events, and so on. Now, as we mentioned, in a fault tree, we're looking at how a hazard occurs due to various failures, various conditions. In an attack tree, we're looking at the probability of a successful attack and how that might be allowed by perhaps failures in our layers of protection. What protections do we have in place, and how might they fail to prevent an attack from causing a hazard? As we've mentioned, there are many similarities between attack tree and a fault tree. Of course, logic gates and basic events construct both of these two model types. And they're also very similar in the way they are analyzed, both qualitatively and quantitatively. In a fault tree, when we talk about qualitative analysis, what we mean is generating minimal cut sets, determining the minimum sets of events that will trigger the hazard of interest. In an attack tree, it's very similar. We're working out the combination of attack and failure of our protective systems that will lead to the successful attack, that hazard that we're interested in. So both of these model types use cut sets to show us the possible paths, the possible causes of a hazard. The quantitative analysis, again, what this means is how we calculate the probability of a hazard, or how we calculate the frequency of the hazard. In a fault tree, simple fault tree, we would generally use a cross product to estimate the frequency of the hazard, and it's exactly the same in an attack tree as well. So the two techniques use similar qualitative and quantitative analysis techniques to determine the paths to the hazard and also the frequency of the hazard. But of course, there will be no point in having a separate analysis technique like attack tree unless there were things that the attack tree could do that we would not ordinarily do in a fault tree. Now, in an attack tree, we're looking at the frequency of a successful attack, but of course, an attack can't happen for free. When an attacker attempts to compromise a system, it will cost them something, whether it's a financial cost, the requirement to acquire specialist equipment, to acquire specialist skills. There will be obstacles to an attacker in much the same way as there are obstacles to us in preventing an attack. And an attack tree can take those things into account. So we're going to demonstrate all of that using just a very simple example. Now, I've based this example on a couple of papers that were presented at conferences in the United States back in August of 2015. The first of these, a paper by Miller and Balasek, and they demonstrated how a car's onboard computer could be accessed via its entertainment system using wireless technology, and how this could be allowed to access systems such as door locks, headlights, brakes, and so on. Now, I think it was accepted that this was a fairly extreme example that they were presenting, but it was kind of a proof of concept to show that it was possible to access a car system this way if it wasn't properly secured. A little later that month, Foster and Kosher also presented a paper on a similar theme, this time hacking into the onboard computer via a diagnostic dongle, something that certainly many American vehicles have installed as part of, I guess, an insurance policy. And this attack could actually be performed using a conventional cell phone, a conventional mobile phone. So what we're going to do is use a software tool to analyze this relatively simple scenario and show what we can get back at the end. So if you'll bear with me for a moment, I'm going to end the slideshow there and move that out of the way and pull up the software tool. So for today's demonstration, I'm going to be using Isograph's attack tree analysis tool. This will give us a framework in which we can build our attack tree, populate it with the relevant quantitative data, and perform the analysis to determine the frequency with which our successful attack will occur. And I'll talk a little bit more about the software later and what you can do if you wish to take a look at it for yourselves. But for now, I'll just get straight in to the demonstration. So the process of constructing an attack tree is very much the same as that for building a fault tree. It's a top-down process where we begin with the hazard of interest, and then we work our way down the tree through the successive levels of cause and effect until we reach the most fundamental events about which we have information, or our basic events. So I'm going to begin by creating a top gate for my tree, which will represent my hazard. So I'll go to add a new top gate, and this I'm just going to call access. And ordinarily, I might add more descriptive information here as well. That would be good practice for me, so I can easily understand my tree when I come back to it later on. For time purposes, I'm not going to type in all of these descriptions here. Maybe once I've finished the tree, I'll just pull up the completed version in a separate file just to show you how this would look with all the descriptive information in place. But for now, I'll just call that access, and that's going to represent successful hacking into the onboard computer of the vehicle. So then I might ask, well, what are the direct causes of this problem? Well, of course, in order for someone to gain access to the entertainment system or whatever system they're trying to get into, there would actually have to be an attack, an attempt to access the system. So I'm going to just create a basic event for that. So I'll add an event and add that beneath my top gate. And I will double click on that and I'll call that attack. Now again, this is a very simplified model. Maybe there will be different types of attack represented by different attack events. I'm sort of condensing it just into one event here for simplicity. But there's an attack against my system, and the other thing that would need to happen in order for this attack to be successful would be for my onboard computer not to be secure. Now, there are many possible reasons that that might happen, so this time, rather than using a basic event, I'm going to add another gate. So I will call that not secure. And in order for the attack to be successful, both of these events must occur together, an attack on an unsecure system. So I will edit my top gate so that that is AND logic. So far, if you've seen a fault tree before, you will have seen much of this too. So what are the vectors for an insecure onboard computer? Well, we said in one of the papers, we talked about someone trying to access the computer via the entertainment system. Well, if my entertainment system isn't properly patched, if it doesn't have the appropriate security patches installed, then it won't be secure. So I'm going to add a basic event for that. Let's call that ENT patch, or the entertainment patch. Again, good practice under normal circumstances, I would be providing detailed descriptions as well, but for time, I'm just keeping it very simple. The other option we said an attacker had was to go via an onboard dongle. A driver may have installed a dongle on the recommendation of their insurance company, maybe to track their driving habits or whatever that it might be. And it might be possible wirelessly to get into the system via this dongle. So I will add this time a gate because I know there are a couple of things that must happen in order to get into the dongle. So I will just call that OBD for onboard dongle. And then below that, I will add 2 more events. I'll shrink that down a little bit so we can see it. One of those is, of course, that the car has one of these dongles installed or connected. And the other is that the dongle has not been properly patched. And of course, again, in order for the attack via this route to be successful, both of these events would have to be occurring together. So this would be AND logic. So again, as we said, if you know about fault trees, how to build a fault tree, the process of building an attack tree will already be very familiar to you. And the next stage, again, much like a fault tree, would be to populate your attack tree with numerical information. So at this stage, it might be worth talking about the concept of initiators and enablers. These are two different types of events, and these are terms that we often use when we're talking about fault trees and event trees as well. An initiator, contrary to maybe what the name might suggest, is the event which must fail last in a sequence in order to trigger a hazard. To give you the simplest example I can think of, an initiator might be the occurrence of a fire. Then, if your fire protection systems are in a failed state at the point that the fire occurs, then there is a hazard. There may be fatalities as a result. However, if the fire occurs prior to any failure of your fire protection systems, then maybe the hazard is mitigated. So the fire would have to happen last in order for there to be a serious problem. Enablers, on the other hand, are events which must fail anywhere but last. So these, in our simplified example, would be our fire protection systems. The failure of the fire protection systems would only lead to a hazard if they occur prior to the occurrence of the fire. If everything is still working when the fire occurs, then of course the hazard may be mitigated. And it's the same principle here when we talk about attack and protection, or attack and defense. If the attack comes prior to any problem with our protection systems, then the attack can be blocked. If the attack comes after the failure of our protection systems, then there may be a successful attack. So typically an attack would be treated as an initiator, and then our layers of protection, the presence of a patch, and so on, might be treated as enablers. So let's open up our attack event. So you can see under probabilistic data, I have the option to choose between initiator and enabler. The attack event is the event that will trigger the hazard as the last in the sequence. So I'm going to enter that as an initiator. And I've got some pre-prepared data where I just say the frequency with which that occurs is once per maybe 10 to the minus 12 hours. Now, obviously, there are questions about where this information would come from. Typically, something like this might be based on information that's been collected in the field. How often have attacks against the system been logged in the last year, 10 years, and so on? So historical information can be very useful for these types of analysis. I'll enter the frequency and click OK. You can see that appears there in the tree. So after that, it's just a matter of entering the information for the enabling events. The enterprise patch, if I open that, I might say, well, that's an enabler. And the probability of a system not being patched properly might be, say, 25%. I'll put 0.25. And again, this might be collected from real-world data, maybe observations of systems made during maintenance, that kind of thing. And of course, something like an OBD dongle being connected or installed, that's information that could even be collected from the organizations who distribute these dongles. So they would know how many of what percentage of their customers are actually using these things. So I'll say 20% of drivers on average might have, 2% of drivers might have the USB dongle installed. And then of those, perhaps again, 25% have not been properly patched as they should be. So again, this is all very much like what we would expect to find in a fault tree. But in what way is an attack tree different from a fault tree? Well, we said that one of the ways in which an attack tree is different from a fault tree is that we can model the obstacles to the attacker, but another is also that we can include the consequences of the successful attack. Now, typically, with a fault tree, if you wanted to model consequences, you would link it to an event tree. In an attack tree, we can model the consequences directly. Now, in the isograph attack tree software, I can define my consequences on the left here. I'm going to create a public safety consequence because, of course, an attack against a privately owned vehicle could result in compromising the safety of the driver, of pedestrians, of other drivers, and so on. So right-click and add a consequence. I could have a whole list of consequences. I'm going to just straight away create the moderate consequence and give that a weight of 5. So I'm saying that the successful attack has only a moderate impact. That's because maybe attacks against things like steering and brakes can only occur at low speed. So the danger is relatively low. So it's unlikely to happen on a motorway while you're driving at 100 kilometers per hour. Maybe it's more likely to happen if you're just parking or moving slowly. The weight is just a dimensionless value that indicates the impact of the problem. This could represent some real thing like a number of fatalities or an amount of money that's been lost, but often it's just a sliding scale. For example, 1 might be the best case and 100 the worst, and the weight is what will allow us to analyze the risk later on. So again, I could have a whole list of potential consequences, maybe minor, moderate, severe, critical, all with different weight values. But again, for time, I'll just create the moderate consequence that I will use here. Then for my top event, I can go to consequences, and for any or all of the consequence categories I've used, I can select the relevant consequence. Here, I'm just doing public safety only. So I'm going to select consequence 2. Now, the other key way in which an attack tree differs from a fault tree is that we can model the difficulty to the attacker. That's handled through what we call indicators. And you can see the indicators here on the left. We've already got a few indicator categories set up. So very common indicators are things like cost. How much will it cost the attacker to attack the system? What's the difficulty? How much skill is required? What equipment will they need? So I can open up the cost indicator, and I can say what the minimum and maximum cost will be in whatever unit of currency I wish that to mean. I can even enter a default value. But the important part is how these values are defined. So typically, let's say I've got 2 possible routes that an attacker can take, maybe the enterprise patch or the dongle patch, attacking an unpatched entertainment system or attacking an unpatched dongle. One might be more expensive than the other. If we have all logic, meaning that the attacker would only need to attack one option or the other, they might be inclined to choose the cheapest. So if the program finds 2 inputs to an OR gate with different costs, then the program will automatically select the lower cost option. And of course, whether it's AND logic, where the attacker would have to take both options or all options in order to complete a successful attack, then the cost will be summed, because the attacker would have to absorb the cost of all the possible routes of attack. And there are similar things here for difficulty. Difficulty is a little bit more difficult naturally to quantify. Here we're just doing a scale of 0 to 10, where the default is 5. And again, all logic is minimum, so that the attacker will choose the easiest option, and we sum where the attacker has to take all options. And for equipment, it's a simple minimum or maximum. If it's AND logic, the program will select the maximum, so it's the most complex, the most difficult to acquire equipment will be used as the benchmark for that gate. So for the difficulty rating, we're doing 0 to 10 with a default of 5, and for the equipment, it's between 0 and 1, and it's minimum or maximum. Sorry, 0 to 100. So once we've done that, we can start telling the program which paths are more difficult, which paths cost more, which paths require the most difficult to acquire equipment. So, for example, if the attacker wanted to attack via the enterprise patch, the entertainment system, the unpatched entertainment system, then the cost might be 1,000. They might need a sophisticated laptop with various difficult to acquire bits of software installed. The difficulty of that attack might be quite high. It might have a difficulty of 10. And the equipment required, that would be 100. Again, because we've got the laptop that we need and all the various different bits of software. And as we said, we need special skills to be able to use all of that. So overall, attacking via an unpatched entertainment system is pretty expensive and pretty difficult route by which to attack. Now, for the dongle, it might be a very different situation. The cost might be relatively low. As we mentioned, with the dongle, all we really need to perform the attack is a phone, maybe a smartphone, and perhaps a particular piece of downloadable software or an app that we can use. The difficulty is going to be somewhat lower because we don't need all the specialist skills, and the equipment level is lower. Again, we don't need the laptop, we don't need all the other bits and pieces, we just need the phone and the app. So attacking via the unpatched dongle, if you can find an unpatched dongle, is going to be the easiest option. So now we basically have a completed attack tree and we can analyze it. Now for that, I might actually switch over to my completed version. Looks a little bit nicer because this one's got all of the descriptions in place, so we can see what we're doing much more easily. So obviously that's much better housekeeping on my part, so I can see what all of that means with much greater ease. So I can run the analysis by clicking the green light button at the top. Then I can take a look at the results. So straight away, I can get the frequency of an expected successful attack and the most likely cost, difficulty, and level of equipment required. And you can see there the program has selected the lowest levels. That's basically the easiest route for the attacker. And if I move across, I can also see not only how frequently an attack will take place, but how much each of the events in my tree contribute to the frequency of that attack. Now, naturally, the contribution from the attack itself is the maximum possible because we have to have an attack before an attack can be successful. But we can look at our protection systems and see where the biggest failings lie. And we can see here that from purely a frequency perspective, the enterprise patch, the entertainment patch is the biggest risk. The sensitivity is basically telling us that we can get the best improvements from our system by improving the security of our entertainment system. I can look at cut sets and see which sets of events, if they occur together, will cause a successful attack. And you can see the entertainment patch attacking the unpatched entertainment system is the most frequent, or the path that's going to be most frequent. But we can also see, well, it has the highest potential frequency, but it's also the most difficult to achieve. Whereas the attack against the dongle is less frequent, but would be easier if attempted. But it's not just the attack itself we can look at. We can look at the consequences of the attack. We can see the frequency of the consequence, the difficulty of causing that consequence. We can see again the contribution of each event to that consequence. You'll notice it's only the same in this case as the gate, but that's only because we have a very simple tree here. But we can also see which sets of events will lead to this consequence as well. And then the risk allows us to weight the frequency by the weight of the consequences that occur. So if I select the public safety option, I can see there is the frequency of the attack against public safety, but there is the risk, and the risk is the weight multiplied by the frequency. And we might find that certain attacks are more frequent than other attacks in their success rate, but maybe the ones with the lower success rate pose a higher risk because the weight is greater. Or maybe a less serious attack, one that we are maybe less inclined to think about, actually happens with so much more frequency that the risk from that lesser attack is actually greater than the risk from what on the surface are more serious attacks. So these risk values can help us to make decisions about where to concentrate our efforts when improving system security. Again, we can see the importance of our various events to our consequence categories and the cut sets that lead to them. So I'm going to move that to one side and bring back our slides. So to conclude, an attack tree analysis can be a useful means to help us understand and model threats. We've shown there how we can model a threat by constructing a tree very similar to a fault tree. And just like a fault tree, which through that process of top-down construction can help us to understand the faults and failures and how they interact within our system, so can an attack tree help us to understand the various attack vectors and various vulnerabilities in our system as well. An attack tree can help us to predict the frequency of a successful attack and the causes of a successful attack. But not only that, but through these things like the importance analysis, it can help us to pinpoint weaknesses, see which events, which protection systems are the most vulnerable, and also to see where we can achieve the greatest improvement by improving a protection system. And finally, where in particular we differ from a fault tree, we can look not only at our obstacles where we need to improve, we can also look at the obstacles that are faced by an attacker, because we might look at a cut set and see, well, the attack would be successful if the attacker went via this route. We might also look and say, yes, but that would be prohibitively expensive, or they would need highly specialist skills, things that are very uncommon. So we can weight the decisions that we make not only by frequency and risk, but also by potential obstacles faced by someone who might try to attack our system. So last couple of slides. Firstly, just to show you a couple of references, some further reading if you wanted to go and look into it. There is the first publication to talk in detail about attack trees. That's the book at the top by E. Amoroso. Then the two papers that I mentioned, Miller and Vasilek from the Black Hat Conference in 2015, and Foster and Kosher from the Usenix Security Symposium also in 2015. So that might be some useful further reading as well. Otherwise, I'll just leave you with some contact information. We have our website, isograph.com, where you can go if you want to find out more information about the attack tree software I've been using today. It's also possible to download a demonstration version of the tool as well. So you can download that and give it a try. And if you have any questions, whether it's questions about pricing or whether it's questions about maybe getting an evaluation license, you can contact sales@isograph.com. So I think all that's left is for me to say thank you very much for attending today's webinar. And are there any questions? Again, questions can be given via the text box or the question box in your GoToWebinar console. Yep, so again, just to answer a question that's come up, if you go to our website, isograph.com, you can download a copy. You can download a copy of the software from there. So another question, would there be a use for event trees in modeling cyber threats? Interestingly, that's a very good question. We have recently, in the latest version of the software, version 3, implemented a facility called a mitigation tree. A mitigation tree is to an event tree as an attack tree is to a fault tree. A mitigation tree allows you to look at the possible outcomes of success and failure of your mitigating systems to prevent an attack. So certainly an event tree could be used for modeling cyber threats, and the latest version of our tool includes something called mitigation trees, which is basically exactly that. It's like an attack tree version of an event tree. Another question. So this example, yeah, that's right, this was a small example, but of course in the real world you may be building much larger, much more complex examples. One of the things that you can do, so let me go back to the start. So we've said, a very small example, the program will not limit the number of gates and events that you can put into a tree. So there is no upper limit. The program won't say you can't have more than 1,000 or more than 10,000 gates. And on top of that, the software is available as a 64-bit application. So you shouldn't run into any serious memory issues while you're running these large analyses. And of course, the tool has other facilities to help you to deal with complex analyses, things like the ability to break your tree down into pages, to search and find and replace in a grid layout. So there's lots of options there. So there's lots of questions coming in now, so I'll see if I can go through as many of these as possible. In principle, yes. So one question that's come in here, would it be possible to use the results of attack trees in a traditional fault tree to calculate the unavailability of a site due to a cyber attack? In principle, that would be possible. More it would be the frequency of an outage due to a cyber attack. The presence of, because in an attack tree, your top gate is effectively an initiator. This is because your attack is an initiator and has no probability value associated with it, only a frequency value. So because there's no probability coming from that event, generally what that would mean is your top gate would only have a frequency as well. And so if you fed that into your fault tree, what you would get at the top is the frequency with which your system would be out of service due to cyber attacks. But in principle, you certainly could include the output from a attack tree in a fault tree as well. So, yeah, another very good question. Is attack tree analysis related to a current safety standard in development? In fact, it is, and it's actually rather relevant to the example that I've been talking about today. The one that springs to mind is a standard that's currently in development. It's the Cybersecurity Guidebook for Cyber Physical Vehicle Systems, J3061. It's an SAE international standard, J3061. I don't think it's available for purchase yet, but it is currently in development. So generic data, no, I'm not aware of any generic industry sources for the kind of information that we used here today. The examples I gave, some of them were estimated. The actual percentage number of dongles installed that I used was actually estimated from some numbers I was able to find online regarding the number of vehicles in the United States that have that type of dongle installed. So I think that kind of information, statistics collected from the field or from papers and things like that, might be your best bet in that scenario, but I'm afraid I don't know of any generic industry sources. Is it possible to exchange information between RWB and the attack tree? I believe it is. I think certainly the import and export would allow you to do that because the fault tree and the attack tree are actually structured in the exact same way. So much of that information will be compatible between the two. Okay, so we'll take one last question. It's quite a long one. So is a minimum, let's see. Yes, there's actually a few questions in there. So firstly, are the minimal cut sets dependent on the indicators? So no, the cut sets are not dependent on the indicators. The cut sets are calculated in the exact same way as they would be for a fault tree. The program then looks at the events that are in that cut set and uses them to determine what the relevant indicators are for that set. So you can look at a cut set and that's been generated independently with its frequency and say, well, okay, there's the expected frequency with which that attack would be successful. But then you can look at the indicators and decide, you know, well, actually, is this going to be prohibitively expensive, or is it actually a very easy path to attack? And then do you have different cut sets for the different consequences? Yes, so we actually showed that. I can maybe pull that back up. Let me move the questions to one side for a moment. So if I bring back the results and I look at the consequences, you can see here it's possible for each individual consequence to see what the cut sets will be. So I think that there may be one or two more questions, but let me see if I can pull those back and answer those quickly for you before we bring things to a close. Yeah, well, the probability that we're using is just a flat probability, and then that's working out the frequency from the probability and frequency. So there's not really much complex sort of statistical distribution in the information that's being calculated. Basically, the frequency of a cut set and so in a cut set, the frequency and the probabilities of the events are multiplied together to simply give the frequency of that set. So it's actually quite a simple calculation. So I think that's the last question that we'll take for today. If there are any more questions, you can certainly get in touch with us. You have the sales contact on the slide. You can send any questions you have, commercial or otherwise, to that address, and we will follow up with you as soon as possible. So again, thank you very much for joining us today. This video will be made available, this webinar will be made available as a video later today or later this week when you'll be able to watch this at your leisure. Thanks very much again, and have a good day.